In section 4.6, we will explore rational functions and their graphs. First, let's talk about what a rational function is. A rational function is a function that is a quotient of two polynomials. So written in symbolic form, f of x would be a rational function if it is equal to the polynomial p of x divided by the polynomial q of x. In fact, the word rational in mathematics has the root word ratio, which is synonymous with fraction. After all, we can say a ratio is a quantity A compared to a quantity B, or equivalently, A over B. Rational functions, therefore, are functions that can be written as the ratio of two polynomials. Because we are dividing, it's very important that we are aware of any values of x that would cause the denominator to be 0 because division by 0 is not defined. We'll explore what happens for these x values that cause the denominator to be equal to 0. For now, we'll just say that the domain of the function f consists of all values of x for which the denominator is not 0. In the graphs of rational functions, we will see some invisible lines that will serve as barriers called asymptotes. Asymptotes are lines or walls that cannot be touched or crossed over. There are vertical asymptotes and horizontal asymptotes. A vertical asymptote for a rational function is found by determining the values of x that cause the denominator to be 0, but that aren't also zeros of the numerator. We're going to explore these values later on in this lesson. So if there's a value of x that causes the denominator to be 0, but not the numerator, then this will identify a vertical asymptote. Because these are vertical lines, their equations will have the form x equals a, where a is a 0 of the denominator. Separately, let's talk about horizontal asymptotes. Horizontal asymptotes can occur in a couple of different ways. When the degree of the polynomial in the numerator is the same as the degree of the polynomial in the denominator, then the line y equals a over b will be a horizontal asymptote. A is the leading coefficient of the numerator, b is the leading coefficient of the denominator. When the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote will be the x-axis, which is the same as the y equals 0 line. Finally, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Let's explore these asymptotes in the next few examples. In our first example, we have g of x is equal to x squared minus 100 divided by x minus 2 times x plus 4. Notice that even if we were to factor the numerator as x plus 10 times x minus 10, there are no matching factors in the denominator, so there will be no shared zeros between the numerator and the denominator. That means that for the vertical asymptotes, we can find the two values of x that cause the denominator to be 0. So when x minus 2 is 0, we get that x is 2. When x plus 4 is 0, we get that x is negative 4. These are going to be the equations of the two vertical asymptotes for this rational function. Again, simply setting the denominator to be equal to 0 and making sure that any of these values don't match any of the zeros in the numerator. Now, for the horizontal asymptote, we see that the degree of the numerator is 2 And after multiplying the denominator out, we see that the degree of the denominator would also be 2. In fact, the denominator can be written as x squared plus 2x minus 8. The leading coefficient of the numerator is an implied 1, and the leading coefficient of the denominator is also an implied 1. So we do have a horizontal asymptote at the line y equals 1 over 1, which is just y equals 1. In the second example, we have f of x is equal to x minus 1 over the quantity x squared plus 8. Here, there's no factoring that's possible because the numerator and the denominator are both prime. So let's find the vertical asymptotes if there are any. First, we set the denominator equal to 0, and we see that there aren't going to be any real values of x that when squared equal negative 8. That means that there is going to be no horizontal asymptote in this example. There is no value of x, at least no real value of x, that would cause the denominator to be 0. Let's see if there are any horizontal asymptotes. We see that the degree of the numerator is an invisible 1, and the degree of the denominator is 2. Because the degree of the numerator is smaller than the degree of the denominator, from our notes above, the horizontal asymptote will be the x-axis or the y equals 0 line. Next, let's look at g of x equal to x minus 11 over x squared minus 1. Here in the denominator, if we set x squared minus 1 equal to 0, we see that x squared must equal 1, and x must be plus or minus the square root of 1, which is plus or minus 1. So we have two vertical asymptotes. Note that none of these are the same as any zeros in the numerator. So we have x equals negative 1 is one of the vertical asymptotes, and x equals positive 1 is another. In terms of the degrees of the numerator and the denominator, the degree of the numerator is 1, the degree of the denominator is 2. Because the degree of the numerator is smaller than the degree of the denominator, again, the horizontal asymptote will be the x-axis or the y equals 0 line. In example 4, we have g of x is equal to x squared plus 4x divided by the quantity x squared minus 5x minus 36. Let's go ahead and factor to make sure that we address any possible matching factors. In the numerator, we have x times x plus 4. In the denominator, this will factor as x minus 9 times x plus 4. And we do see that there is a matching factor of x plus 4. Because negative 4 here will be a matching 0, we will not generate a vertical asymptote at x equals negative 4. The vertical asymptotes only occur for zeros of the denominator that are not also zeros of the numerator. But we will see one vertical asymptote for x minus 9 equals 0, which is x equals 9. For the possible horizontal asymptote, let's compare the degree of the numerator to the degree of the denominator. We see that the degree of the numerator is 2, and that matches the degree of the denominator, which is also 2. That means that we will have a horizontal asymptote where we have y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. In both of these cases, an implied 1. That means that the horizontal asymptote will be y equals 1 over 1, which is just 1. Later on in this lesson, we will discuss what happens when there are matching zeros or matching factors in the numerator and the denominator. It's going to create something known as a removable discontinuity, which we also just call a hole in the graph.